Oh, here we go. The recording started. So when we subtract input and the output of the neural network and it's 0, it means according to that neural network, there are no artifacts. Okay, so there is an interpretation. The fixed point of this operator has some form of interpretation. That's interesting. And then here, of course, when the gradient is 0, means we got the minimizer of the cost. And then this G tries to incorporate them both into a single algorithm. Okay. Any questions so far? All right. So let me say that. So those are both forms of the algorithm. Let me say one of my most interested things, and I won't really go deep into this, unfortunately, because this, I've been exploring this over several publications, but I think it's a fascinating topic, and some of you, some people who are already working it or find it interesting, let me mention this. So suppose there is a vector that exists at the intersection of the fixed point of artifact removal operator and a 0 set of the gradient, right? Suppose there exists a vector. How could we interpret that vector, right? So what's the fixed point of that operator? It means input and output are the same. What's the 0 set of it? It's a set where the gradient is equal to 0, right? If indeed there is such a vector, it means that vector is both consistent with the measurements, right? Because you perfectly minimize the data fidelity term, right? If it is convex. If it's not convex, okay, it's a stationary point. Or you find it's artifact free according to the prior, right? So this is in the case where intersection is exactly 0. If intersection is not exactly 0, essentially you're finding an equilibrium between those two, where control of the balance is controlled by tau parameter in the rare algorithm. So then, based on some kind of interpretation like this, you can write all kind of interesting things about this. This is just one form of it. There are many other versions for weakly convex, strongly convex settings, for non-expansive neural networks, for contracted neural networks, for contractions at the residual level, and so on. But here, let me just state one case where we assume that G is convex and Lipschitz continuous, which is standard in optimization. And I'm going to assume that artifact removal operator is a contraction. Okay, so R operator is a contraction, and then Lipschitz continuous, I guess many people know, it just simply means that difference of the outputs is bounded by difference of the inputs. So if you do this, basically plug and play and red will both converge, and both will converge to a vector at the intersection of the sets, or meaning converge to a vector of this form. Okay, this is just one form of the state. In this case, plug and play and red will be equivalent. In fact, they were invented as separate algorithms, but in fact, they could be equivalent under some conditions. And then you can also state all kinds of different convergence results and so on. And if anybody is interested in this, one of the latest papers we did on that was this recovery analysis paper, which is on archive right now. It's under review at NeurIPS for this year. All right, so any questions so far?
Maybe I can take the opportunity to ask you one question. So,
sure.
Did you study stability? This was related to what we discussed before, but if you have noise, can you establish stability?
Noise in the measurements?
Yes.
Yeah, so you can establish stability in some sense. So I mean, it's pretty technical. So that's what I was trying to tell you, Pierre, saying that I think it's an interesting problem to go. It's much deeper than I have looked at. Okay, basically what I want to say is that by taking this work of Vershnin, you mentioned Trop, compressive sensing literature, you can try to connect analysis like this, meaning monotone operator theory, which is very old, to interpretation of neural networks through their fixed points. And through that, related to compressive sensing theory by looking at randomized operators and so on. A quite superficial look at it is presented in this manuscript if anybody's interested. But I'm very happy to discuss with anybody who is also interested in that direction. And maybe we can talk in Brasserie more about this later. But you can have stability results where you bound your result in terms of the error in your measurement recovery bounds.
I see. Okay, thank you.
You're welcome. Any other questions? All right, so this is just to give you a flavor, by the way, but really rigorous foundation, I think, is in monotone operator theory, which is beautiful. You know, there is Bauschke Combat book, which is always on my desk, which is pretty dense, but very nice to look in when you look into monotone operator theory. And another thing I wanted to mention is that now the second thing, so why did I kind of call it regularization by artifact removal, not regularization by denoising? The reason was to try to go out of the restriction of being a denoiser. I think there is no reason for plug and play to be restricted by denoiser, and I think we should give up with that narrative. And there is no reason for red to be regularization by denoising. Okay, the denoiser is linked to proximal optimization, but if you're not using proximals, there is no need to restrict yourself to denoising. Okay, and then one advantage of going beyond denoising is to try to design priors that don't use ground truths. And this was very useful for us in the context of MRI. So in the ideal world, we have available data. So we have data with noise, right, or some artifacts. Then we have some ground truths for training, the reference, and we can train the neural network. Now, in some cases, at least in the MRI with motion, so a free breathing MRI, we might not have ground truths. You know, there is no moment where a person is stationary where you would have a perfect ground truths. In that case, what we do have is two artifact corrupted versions of the image, meaning what? You take all the k-space measurements, you can divide them into two, right? Where you have one and the second artifact corrupted image, right? But you don't have a ground truth training label. So instead of training with a ground truth, a simple strategy, which we called artifact to artifact, which is inspired from noise to noise. I don't know if anybody is familiar with noise to noise. Probably many people are. It's made quite an impact. It's a very elegant paper that looked at the idea of saying if your images are structured and you add completely random noise to it and you train on it, in fact, your loss function is essentially the same, and you can train it as if you're training without noise. Of course, there are assumptions there. The key assumption is that in expectation, the expected value of the noise is 0 across all the measurements. And the second assumption they have in the paper is on the fact that the training loss is L2, so Euclidean loss. If you have those two, then you can get their kind of theoretical results. But the idea can be, in fact, again, generalized to the case where now I don't have noise, I have artifacts, right? So long those artifacts behave well, meaning in expectation, if I take expected value for all the artifacts, it is 0 across the data set, right? Then you can again train the CNN without any fully sampled ground truth. And this is very useful in applications where you don't have it, okay? And then the key is, and that's what I want to show you next, is the best of the world is not just to use this neural network, but to use it as a regularizer, as a prior for image reconstruction. So here's some results on experimental data for reconstructing 10 breathing motion phases from a 1-minute free breathing MRI scan. So what do I mean this? You have one 3D scan. We want to split it into 4D, whereas the fourth dimension is 10 images. You have 10 3D images. Each one is a different breathing cycle. Okay. Now, what happens, you can imagine, it's going to be heavily subsampled because you're dividing it into 10. It's a 1-minute scan. And then what if you would do inverse Fourier transform, you would see something like that. That's a result of inverse Fourier transform. If you would do a traditional compressive sensing reconstruction, meaning regularized, total variation regularized, from 5-minute scan, you would see something like that. This is a 5-minute scan. We call it reference, right? It's not ground truth because it's still subsample. That's the best we can do, but it's somehow gives us a higher quality reference. So this is a reference image here. This is training a unit, 3-dimensional unit, to map MC and inverse FFT images, right? Zero field images to the reference. So you use this as a label, you train this is something you would get. If I train without any ground truths, meaning I have 1 minute, so it's a total 5-minute data, I can divide it into 5 1-minute datas, randomly reassigning spokes, and I train it just on artifact corrupted data, I would see something like that, right? You see, it's still not as good as this, what we have reference or unit 3D. It still have some streaks, but it significantly improves over MC and FFT. And finally, if I put it as a prior into the regularization by artifact removal, I would see something like this that improves. Now, the numbers on the top right are SNRs, but take them with a grain of salt. They're computed relative to reference. So it's not really true SNR. it's the best guess we can have for us. Okay. Here's another example of the same thing. Here's artifact to artifact training with only artifact corrupted images. And then here by using as a prior, and here's a reference, right? So you can see it significantly improves in any case compared to the original MCNF50 data. This is just to show you the evolution of the image. So iteration 0 is the output of this neural network. So we already get a good initialization. And as you iterate, you basically refine the solution by bringing back information from the forward model, right? You bring it back and you iterate. So you kind of refine it to get to iteration 9. Any questions so far? There's a question in the chat. Let me actually read it myself. So the first question is, using a denoiser in the plug and play or red is often interpreted using 3D formula. Okay, something that we'll lose with another artifact remover. Yes, definitely. But in fact, I think that's a weakness of 3D formula. It's not, 3D formula is a pretty elegant concept. It's a very elegant concept, but it's only true for certain types of noise. And in particular, the very elegant formula comes for additive white Gaussian noise. So if for your theoretical analysis, it's useful, it's great. But so long you don't satisfy the assumption of noise being that, you don't have 3D's formula to be exactly valid, right? So there is kind of 3D's formulas comes with its own assumptions. It's not that we lose it by moving out. It's meaning it just 3D's formula restricts us to the range of denoisers. Okay, so that's all I want to say there. And how did you use a network as a regularizer? That's a great question, and it's very simple. This is exactly the algorithm we use. Okay, so this is a network trained that way. We just take residual of it and add it to the gradient. That's how it's used. And for more information on it, please take a look at the paper. You can have more data, more validations, more experiments. Yep, 20 minutes left. Thank you. In any case, I'm pretty much done for this chunk of the talk, but let me just show you that in this paper, we also compared that with using GANs, generative adversarial networks, which have been extensively used. So ILO is a method, which is a very recent method from this year, and Pulse is a method from last year. Both of them essentially do optimization by projecting to the range of generative adversarial network. And this is a style GAN trained on faces, which is pretty, good regularizer. And here we trained a artifact removing network, and here's a denoiser. The reason I'm showing this is just to show you that by going beyond the noisers and training it properly, you can improve over the noising performance. Okay, the noisers are great, but also restrictive when you use them as a prior. Might not be need for you to be restricting yourself to the noisers. Okay, and this is something I wanted to show. This is all in this paper. Again, that relates also to stability of reconstruction, what Pierre was asking, and so on. Feel free to take a look if you're interested. And I think with that, I'm going to close that chapter of my talk. And I want to lose next 10 minutes to just talk briefly about deep unrolling, which is very related to the first part, but has been, I think, much more extensively used in the context of inverse problems. Even the talk before, I saw that it was essentially based on designing model-based neural network by kind of unrolling iterations and training end-to-end. All right, so deep unrolling or deep unfolding is very widely used, right? Here's a simple thing. All you do is you take an algorithm that's iterative and interpret each iteration as a layer of neural network. So I take an iteration of red or rare algorithms that I just talked to you, and I represent it as a block like this, right? So you see R theta here, you have a gradient of G here, and then there's a skip connection because of the X here. So minus gamma tau X gets a skip connection here, okay? So that's one iteration or one layer. I can do it for Q layers, right? And by doing this, I'm going to end up with a neural network. So now I can train end-to-end. So now that neural network can take Y, which is my actual measurement, initialized with a back projected image, and trained, for example, in a supervised way by either using ground truth or by using noise-to-noise type of strategy. Okay. Now, what are some advantages? Well, the key advantage, I'm not going to ask a question here interactively because time is limited. So the key advantage here is I can train end-to-end. Essentially, I can train my artifact removal operator based on the task I want to solve. So it's not anymore as a denoiser, right? What's the disadvantage? Well, the training cost goes up pretty significantly. In fact, if you do traditional plug and play and you train the denoiser, you're just training it on denoising. Here, your training has to include your forward model. In some cases, this forward model is pretty costly. And think of the memory cost of this. You have to fit it all on your GPU or distribute optimize it by putting every layer into GPU and training this end-to-end, right? That's definitely a disadvantage. So yeah, so unrolling enables learning optimal artifact removal CNN, but can have significant complexity costs. And in particular, what I want to talk about is this operation here, which is a forward model. Anytime you involve the forward model, well, you have to involve some form of simulation of a forward model, which could be quite costly. It might limit your scalability, in particular for large-scale problems. So here's a simple solution that we're thinking for problems, and we used it essentially for tomographic settings, right? For optical tomography or for CT tomography, and now we're also using for cone beam tomography. So in the traditional deep unfolding, use batch data fidelity, but we already know that SGD enables us to use mini batches, right? So essentially, the idea of SGD-Net is to train an unfolding or unrolling algorithm by only using stochastic data fidelity terms, right? So we use only subset, mini batches of data fidelity terms every iteration, which means the complexity of physical layer is independent of the number of measurements, right? Because you do stochastic subsampling at every layer. Yeah, so this is a side-by-side comparison. If in the traditional layer I would use full gradient, in SGD-Net we use mini batch gradient, which decouples it. So here's how it would look like, right? So you have the prior here, and then now you have stochastic gradients embedded here that you can train. Now, if you assume your prior is trained, if you just run forward the same, you can still use monotone operator to characterize the convergence of this algorithm. I mean, this is interesting to know, but you know, it just tells us that if everything is fixed and you run this forward inference step in a stochastic way, you're going to have something like a SGD type of convergence. And then this essentially this comes from monotone operator theory. Feel free to take a look at the analysis there. But what's more interesting is the following result, which is part of this paper here. If you design an SGD-Net and train it with SGD, okay, there's like almost like a meta SGD. I have an SGD network and I train it with SGD outside. And then each layer, you do mini batch approximation with mini batch size B, then you can get the fixed or the stationary point of non-stochastic neural network, meaning using all the measurements at every iterations up to an error. And that error depends on the mini batch size, of course. So as mini batch size grows and you know it kind of goes down. So this is an analysis you can do here. Somebody's saying yes, like, oh, okay, we can talk about the questions later. Thanks for answering this. So yeah, so let me just show you an example. This on real data, experimental data on the diffraction tomography. The advantage here was by using mini batch processing, we could really do easily 3D optical diffraction, intensity diffraction tomography, where we could have hundreds of 2D measurements. Each measurement is 1025 by 1025. So it's a pretty big inverse problem. So if you would actually use all the measurements at every iteration, you know, it kind of costs significantly, especially once you need to model scattering effects. But if you do it in this way, you can save quite a bit of computational time and get pretty much similar results as a full rare. And then, you know, there is a savings you can do in the training time because you're training on a stochastic model and so on. You can roughly cut it in two in our implementation, but maybe you can do more. So let me skip those things to leave some time for question and answers, because anybody can look up those in the papers, whoever is interested. Essentially, they're trying to compare what I'm talking about to existing algorithms and try to draw conclusions, empirical conclusions about it. So to kind of wrap up my talk, you know, we increasingly use deep learning, right, to characterize statistical distributions. And here I wanted to use it as a prior. And I talked about two ways to do it. In first case, rare, essentially the focus was to use artifact removal operators and use inexact training data, just like in noise to noise. And in the second part, I talked SGD-Net, which is unfolding that kind of algorithms and using inexact forward models, but randomized inexact forward models, so we can still analyze training of those networks. Okay, so that was the second part of the talk. If anybody is interested to read more, the talk is based on those 3 papers, but by one of my PhD students. So 2020, 21, and the current one under review from NeurIPS. Feel free to look at them. And I think I'm very happy to take any questions at this moment.
Okay, Ulugbek, thanks a lot for this nice talk. So people reacted in the chat. So maybe the first question by Denis Friboulet is, does SGD has convergence properties in the style of Willett's deep equilibrium models?
This is a great question. So, by the way, I really like that deep equilibrium models papers, and I actually write the original concept of deep equilibrium models as well, that deep equilibrium models of Becker is based on. So does it have convergence properties? Yes, in fact, the convergence properties are kind of complementary, right? The convergence properties of deep equilibrium models is essentially the same type of convergence as in monotone operator theory analysis of rare and all those algorithms. It's much more, because essentially they do run the forward pass until the end and run the backward pass until the end, and they get the gradient. And then they say on the properties of neural network, like one expanded, and they can establish convergence of that whole forward pass, the backward pass. So it's very similar to the traditional analysis of plug and play priors. If anybody wants to think about it, here it's a different type of convergence, right? Here I'm not talking about convergence of the gradient estimation. It's a convergence of training of this neural network. Okay, so that randomizedly subsampled neural network. So this is a loss function for training. The gradient of the loss function for training means the stationary points of your loss for training loss, right? What I'm saying is by not using the exact forward model at every layer, you can still get close to the stationary point of a loss using full batch at every layer of CNN. So it's a slightly different angle of analysis than in the deep equilibrium models.
Okay, thank you. So we have time for a few other questions. Actually, we have quite a lot of time.
Oh, that's good.
Anyone in the chat or take? I had one informal question by text message, which was, how do your the rare models compare in terms of performance if you participate to a challenge?
Oh, is it from Philip? Is it from Philip?
No, not at all.
I know that he participates a lot in challenges. I never submitted it to challenge. I don't know. Okay. The short answer is I don't know. So the challenge is a different animal altogether, right? So a lot of the time, when you try to do the challenge, you need to spend more time on optimizing the model and doing a very good work on squeezing out maximum performance. So far, the research I talked about has been a lot about conceptual breaking down of the problem. But definitely, I think it would be interesting to push them to the limit and to actually compare them. How would they compare on FastMR challenge, for example, where some of the methods did really, really well.
Okay. So there is a question which I had also by Samuel Huro. You spoke a lot about monotone operators.
Yeah.
So his question is a bit different. So his question is about, is it restrictive to consider R contractive? Mine would be R monotone, which is even stronger. Well, not really stronger, but.
Yeah. It is so the short answer, it is definitely restrictive, right? It is definitely restrictive. So instead of saying, look, I'm going to train it for, let it evolve the way it wants to and train it, I'm going to make a constrained optimization problem for training, right? I'm constraining the training to make the network contracted. So it is definitely restricted. Now, the question is how much, what's the cost, right? What's the cost? And there are even different papers that are coming out recently that different ideas which are not contractiveness or monotonous, but saying, oh, can I make it a field? So it is a gradient of some operator or things like this, different type of ideas coming out. Each time you put some constraints. So the question is, which constraints for us is good enough? We still get stability, but we don't lose too much in performance. Now, for contraction and for non-expansiveness, we have done a lot of experiments. If you look at the papers, we have comparisons on denoising, on reconstruction empirically, right? What you're going to see is that you typically pay a price. Originally, the price in terms of reconstruction used to be maybe close to dB, 1 dB. But lately, by training a residual network, so training a residual to be non-expansive or contractive, you can get pretty close to the unconstrained neural network. And this is only true for DNCNN because we never tried it on a UNet. We never did this experiments on UNet. So when you track DNCNN and you train it that way, the cost is now less than half a dB, the discrepancy we see when we train with, but in the residual, you have to train a residual network, not a traditional network.
Okay, thank you. And my question was, I didn't spot it exactly where you needed monotonicity of R, but this looks like a strong hypothesis.
Oh, monotonicity of R, yes. So in this case we say, yeah, R is a kind of contraction or a non-expansive. That's what you need.
Yes, but at other places you needed monotonicity, no?
No. Well, it's not the R that needs monotonicity. You need a monotonicity of an update. So there is like a connection between contraction and contraction and monotonicity.
Yes,
they're related to each other. So if an operator and a residual might be another, you can kind of relate those things. It comes into the proof, but like a condition on R, for example, well, this is one condition. It's a contraction of R.
It's enough to.
So basically, think of traditional gradient method, monotone operator theory of traditional gradient method. Essentially, the way it happens, it's the same way, except you lose the fact it's a gradient. Okay, so that's where you need it. That's exactly where you need it. So.
Okay, thank you very much. So other questions? We have time for one or two. Chat.
Maybe I can ask a question, Pierre?
Yes, of course.
Thank you, Ulugbek. It was a great talk. I really enjoyed it. I have a question that is at most partially related to what you presented. So in this paper that you have referenced a couple of times, which is also on this slide with this recovery analysis, if I understood it correctly, you're working with a condition where you assume that you have an RIP basically on the image of a neural network. Would you do you think that this is an assumption that is typically satisfied, or an assumption that is rather difficult to be satisfied?
Yeah, so this is a great question that haunts us since 2005 in general for RIP, right? Is RIP, when does RIP is generally satisfied, including for sparse vectors? I mean, we have understanding for randomized random matrices and so on. Here it's the same thing, right? In fact, if you look at the paper, my analysis is even weaker than that. Right? What do I mean by weaker? If you read Dimakis, Bora et al. Papers that Andres referenced there, right? They say, oh, you need restricted strong convexity that for a generative model with a latent space of dimension k, you can have under this sample complexity. So in this paper we submitted, there is no that link to sample complexity. We're still missing it. We're getting there, but we're still missing it. Okay, so that's a nice thing. But on the other hand, when does it satisfy? And I think I don't have, well, it will eventually, I think eventually we're going to have a theory that it will be satisfied for some sample complexity on a random Gaussian models, okay, random Gaussian measurement models. Is this useful? Well, conceptually, theoretically, not in MRI so much, not in CT so much, so that it will still be a very big subset of an inverse problems. But in my opinion, the reason I'm still interested in it, it will complete our conceptual understanding of priors from compressive sensing to now to deep priors. So I'm sorry it's unsatisfactory, including for me. I don't have the full answers, but this is the best statement I can have is that whenever compressive sensing theory will be true, hopefully we can have statements with deep priors.
But so if I understood you correctly, you would link or you would see the difficulty rather in the random matrix theory. So you would rather say it's not clear if it's satisfied because of the measurement matrix. You wouldn't really see it in that the image of a neural network could be arbitrarily complicated, and maybe there are so weird outputs generated by a neural network where you don't have this property that you set and keep the norms.
I'm sorry, I misunderstood. It's a great question, by the way. Yeah, so the question is, what's the complexity of the output of the neural network? In fact, this is a nice thing. Whenever we talk about deep learning, we can, in fact, control the neural networks we use. I think that's a strength of deep learning. So how can we control complexity of the output of neural network? Well, just like Dimakis does. For example, they use Obora et al. They use a generative model with k-space latent space. Well, now you can imagine training a bottleneck neural networks where a bottleneck layer is k-dimensional. What does this mean? The output will be restricted to be synthesized from k-dimensional vectors. And I think that's an interesting direction. So designing neural networks with restricted range space such that interaction with the measurement matrix will be well behaved.
Thank you very much. Thank you. Very interesting.